Welcome to lecture 10 of the NITheCS SATACS category theory course. This is the last lecture of the course, but of course, this is not the last topic of category theory. The subject is extremely large since it connects with many areas of mathematics. So I had to decide what to pick for this last lecture. And indeed, there are many fundamental topics we have not covered. So it's not easy to make this choice. But eventually, I ended up on the topic that at least we will begin with today. So one of the very basic ideas in mathematics is the idea of equality. When two things are said to be equal to each other. Now, of course, when we study mathematics, we are kind of thinking of equality as being the same, right? That two things are identical to each other. But then, if you think deeper a bit about it, you might realize that equality is not just about being the same. It does a bit more than that. It's a bit of an abstraction of being the same. So, for example, when we say that number one equals, well, let's say number two equals 1 plus 1. What we mean here is clear, right? But for someone who hasn't seen numbers yet, who thinks in terms of numbers, who thinks of numbers in terms of actual physical objects, in terms of quantity, for such a person, number two would be a quantity of two things. And then this equality expresses the idea that if you take one apple and if you put together with another one, you will get the same quantity. So if this quantity of apples and this quantity of apples is combined, you will get the same quantity as this one. And of course, when we think of it this way, these apples on the left side and the right side no longer have to be the same. They don't have to be the same apple. It's just the quantities that are the same, right? And the quantity itself is an abstract concept. So it's not about equality of two things anymore at this level, but rather it's about having some common abstract feature. In set theory, we have a nice way of expressing that, right? If we take a single element set and we take its, let's talk about it category theoretically. If we take its coproduct or sum with another single element set, so each of these sets have one element, then we will get a set that is isomorphic to a two-element set. In other words, bijective, right? So in the category.
May I ask something?
Yes.
So what this actually reminds me, maybe I'm understanding it false, but still what it reminds me is in Wolfram Mathematica, for example, and I suppose in other programming languages, we can use, instead of two equality signs, for example, in the uppercase, 2 is equal 1 plus 1, it will return us true, because its values, these two expressions are equal. But in Wolfram Mathematica, we as well have three equality signs. And it means that two expressions should be equal without any further manipulation. Is it what you're talking about? Or?
Yes, this is very similar to what I'm talking about. Indeed. Well, I tried to kind of use this real-life explanation of numbers to motivate this, but I could have also used logic. I could have said, think of number 2 as a logical, as a syntactic expression. So it's just a sequence of symbols. And of course, then this sequence of symbols and this sequence of symbols, they're not the same. They look different, right? And this is what you're talking about. But they evaluate to the same number. So this is another example of the same phenomenon I was trying to explain. So what you said is a nice second way of viewing what I'm trying to explain. Does that make sense?
Yeah, it does. Thanks.
Mm-hmm. And indeed, I mean, this example that you gave goes further, right? So, for instance, if I have a logical statement of the form A and B, so A says something, B says something, and now we're saying A is true and B is true. Is that equal to B and A? Well, if we want to form a Boolean algebra of our statements, we will have to force them equal. So we will have to make some kind of a congruence and then quotient out by that congruence. But if I write these expressions out, they're not going to be equal. They're going to be equivalent to each other, right? We usually express it like this, yeah? For instance, if I form, I mean, I can, so this also enters set theory. If I form the set of those x's such that x is in A and x is in B, which is the set of the intersection of the two sets, that will be the same as the set of those x's such that x is in B and x is in A, and that's the same as B intersected with A. And this is a kind of a proof that A intersected with B as a set equals B intersected with A. But in this proof, we have to, at some point, show that this statement, and then we will say, not equals, but is equivalent to this statement. In other words, the truth values of this are exactly the same as truth values of this. If I set up a truth table for this that depends on the truth values of A or B separately, I will get the same table as if I set up for this one. So that's again about values being equal as opposed to expressions being equal. So that's another, yet another kind of manifestation of the same phenomenon. And then, so, but now, of course, both this level and this level is also mathematical. This is not mathematics, right? This is apples. And the reason why this is not mathematics is that it's not abstract enough. We cannot actually describe an apple, a concrete apple. We don't know how to describe it mathematically. Describing it mathematically would mean describing it fully. All of its physics, all of its chemistry, all the features of the apple would have to be encoded mathematically. And we don't know how to do that because we don't understand the universe up to that level of detail, right? So we can only abstract things when we describe them mathematically. And a very rough way of abstracting this is to think of quantity only. So forget about apples completely. So this thing is not mathematical in that sense, but this is mathematical, and this is also mathematical. And already here we see that another kind of equality emerges, which is bijectivity of two sets. Just like here in mathematical logic, another kind of equality emerges, which is equivalence of statements.
So this also reminds me of quantitative natural deduction. So equality. So you can have a logical system which is both sound and complete without equality. But yeah, so equality is not an important thing in that way, but
yeah,
it's good to have.
Yeah. So yes, indeed, you can actually do a lot of mathematics without equality. In a logical system, equality has a property that it allows you to substitute things. So how do you define equality in mathematics? So if I have x equals y, then everywhere I'm encountering y, I can replace that y with the x, and the two statements will be equivalent to each other, and that can be seen as a definition of equality. And that axiom is quite strong. I might not want to just establish this transformation by substitution. I might want to decompose my statement into smaller bits, and each of them replace them with equivalent ones, and then recompose the bigger statement, something like that. Anyhow, so I began with equality, and then I introduced this idea of bijectivity. Now, and of course, in logic, we have this idea of equivalence, but let me go back to set theory. So the notion of bijectivity between sets, in a sense, plays a similar role as in the theory of sets. It plays a similar role as the notion of equality does when we work with arithmetic, when we work with basic arithmetic. And this picture here kind of shows the link between the two, of course. But of course, in set theory, we also want equality of sets, right? Now, when we move to the level of category theory, when we're viewing sets as objects in a category, we do have there the notion of equality, of course. We can say that two objects are equal. And we also have a notion of bijectivity, and that is isomorphism, right? So there are morphisms going back and forth, F and F inverse, and they're such that their composites on each side give us the corresponding identity morphisms. Now, this notion of isomorphism ends up playing a bit more important role than the notion of equality when we view sets as a category. And the reason for that is that in some sense, so remember, the purpose of category theory in a way is to understand the organization of mathematical structures of a similar type. And then you want to have a concept which will tell you that two structures are same enough. So they have all the same properties, the two of them. And we encounter a lot of examples of situations like this. Like for instance, if I take a vector, vector spaces, right? I could take the vector space R cross R, two-dimensional vector space, or I could take a vector space R cross R cross a singleton zero. So let's think of a plane embedded in a three-dimensional space. And of course, these two vector spaces, they will be the same in the sense that they will be isomorphic with each other. And even something like commutativity of addition, as we discussed earlier in another lecture, if I take two objects, A and B, A plus B in a category will not be equal, but it will be isomorphic to B plus A. And we have similarly for associativity, these two expressions will be isomorphic to each other. So the role that equality played in arithmetic when we were abstracting things to only quantity, here, since we don't have just quantity, we have the actual ingredients, we no longer want things to be equal, we want them to be isomorphic, because we want the quantity of the elements to be the same. But it doesn't mean that they're equal. Okay, so in a way, consideration of mathematical structures, and of course numbers form a structure themselves, right? Consideration of mathematical structures brings us to this idea that now we need a second kind of equality, which is a bit more relaxed notion than the strict equality we knew about before, and which will be telling me that two mathematical structures are basically the same. Now, we are organizing these mathematical structures in categories. So let's make a picture like this. So concrete mathematical objects. Of course, every concrete mathematical object is actually an abstraction of concrete real-life objects. So we have this arrow of abstraction here. And equality lives somewhere here, right? An example of a concrete mathematical object, for the purpose of what I'm trying to explain here, would be numbers, for instance, 1, 2, and so on. Now, these concrete mathematical objects, they often organize themselves into mathematical structures. So we can call these concrete mathematical structures. And for example, here an example would be the group of integers, or the vector space of reals, and so on. And again, some sort of abstraction is happening here. And at this level, we do have equality, but another player, an important player, comes in, which is isomorphism. So this is equality, and the other one is isomorphism. When I'm working inside a mathematical structure that consists of some ingredients, some elements, right? What I care about is when two elements are equal to each other. But when I'm working with two different mathematical structures, what I care about is not whether they're equal or not. That is less important. What I care about is whether they're isomorphic or not, right? Now, you see a mathematical structure. Okay, so a concrete mathematical object, let me represent it as a point, because when I say concrete mathematical object, what I mean is a mathematical object that doesn't have more contents inside it. But of course, in real life, it does, because it's an abstraction of some real life idea. So it decomposes into things of real life in a way. For instance, I can think of number 2 as the collection of all possible 2-element sets of real life objects. Okay. Now, a mathematical structure also has ingredients. A single mathematical structure also has ingredients, but its ingredients are concrete mathematical objects. Okay. Now, at the next level of concrete categories, our category has ingredients as well. A concrete category, like let's say the category of groups, for instance, or the category of vector spaces, it has ingredients, right? Its objects are mathematical structures, so its ingredients come from the level below. And of course, there is more than that we also have morphisms that are ingredients. And inside a category, if I work inside a category, I do have equality, and I even have isomorphism, right? Remember, when I work inside a concrete mathematical structure, like the group of integers, I have the notion of equality of numbers. So this is happening inside. This is internal. Whereas isomorphism is external, because I cannot talk about isomorphism of two numbers. I can only talk about isomorphism of two groups. So it's something happening across mathematical structures. In the same way here, in a category, in a concrete category now, both equality and isomorphism become internal. Now, and there is something external now, I want to explain that, but if I go back one step below, I said that isomorphism is external, but we also have external equality, right? We can talk about equality of structures, even though I said that's less important, but we have it. We have external equality as well. So this is internal equality. When I compare two elements of a structure, I decide whether they're equal or not. And this is external equality when I decide whether two structures themselves are equal or not. In the same way here, we have external equality and isomorphism, and this will be equality and isomorphism of categories. But we also have something third. And there isn't a fixed notation for it, this third one. So I'm just going to use one of the standard notations, something like this. And this is called equivalence of categories. And this would be that two categories are essentially the same. They're not going to be isomorphic. It's more relaxed notion than isomorphism. And it's interesting how we'll be able to define something even more relaxed, but maybe even more useful than an isomorphism. Does this picture make sense? Can I move on?
So where do functors fit in this picture?
We need functors to define isomorphism of categories, right? And we will now look into that just now. So we need functors to define what is an isomorphism of categories. It will be two functors going back and forth, so that when I compose them, there are identities on both sides. So functors will be useful for this.
Okay.
But we need something else, another ingredient than a functor, as we will now see, to define equivalence. Okay, Alexander, are you happy with this picture? Can I move on now to spell out the details, what I'm trying to say?
Yeah, it looks beautiful.
Okay, great, thanks. Okay. So first, let us look at a couple of examples of comparing two categories before we state the definition of an isomorphism of categories, and then this more general notion of an equivalence of categories. I think a classical one would be, well, there are a few things that can be called classical. Okay, so let's first give an example of equality. So I've got the category of sets. And the category of sets is equal to the category of sets. Now let's look at an example of isomorphism of categories. I could consider the category of monoids. So what are monoids? They are triples, x dot 1, where dot is an associative operation on a set X, on this set X, and 1 is an identity element for this operation. This category is no longer equal to the category of, and let me call this thing mon with a subscript 1, and let me call just mon a category of pairs of a set X, associative operation defined on it, for which identity element exists. Okay, so these are sets with an associative dot for which identity element exists. And here, the difference is that here we've specified an identity element. Now, it turns out that in any monoid, when you have an identity element in a monoid, you do, if you remove it, it's going to be called a semigroup, right? So in every monoid, it turns out that there is exactly one identity element, and the proof is very simple. If 1 is an identity element, it will be equal to 1 times 1 prime, where 1 prime is potential another identity element, but because so this is because 1 prime is an identity element, right? But because 1 is an identity element, this will be further equal to 1 prime. So 2 identity elements will always be equal to each other. And that means that if I have this monoid, so monoid specified as a pair, right? It can be, it will give rise to me, of course, to this one, but it will give rise to me to this one in a unique way because the third element is always unique. So there will be bijection between these triples and these pairs, and of course the homomorphism property will be also preserved by this. So there will be what is called an isomorphism of categories. Now, of course, we have to. So unlike in groups, if a homomorphism preserves multiplication, it will not automatically preserve identity. So I have to specify that. So maybe a more interesting example, more illustrative example would have been if I said groups here. Groups with specified identity and groups without specified identity. And I can do something third, which will be groups with specified inverses for every element. And that is also unique, as we know. So a group homomorphism then is defined as a map that preserves multiplication. And it turns out that if a map between groups preserves multiplication, then it will also preserve identity element. So what we will get will be that I can move back and forth between these two categories. So I'll have a process going this way that maps every triple x dot 1 to x dot. And I have also a process going backwards that maps x dot to x dot 1. And these two maps are inverses of each other. So we have this isomorphic situation. But of course, categories are more than just sets of objects, right? Or classes of objects. They also have morphisms and composition. And we want these kinds of mappings to preserve such things, and such a thing is called a functor. So if I have a morphism of these kinds of groups, let me call this x prime dot prime, and then x double prime dot double prime, and this is a group homomorphism f and g. When I map this to x dot 1, and I map the other one to x prime dot prime, and then let's call this thing 1 prime, and I map this one to x prime dot double prime, x double prime dot double prime, 1 double prime. The same maps f and g will be also homomorphisms on this side. And then because of that, also the composition will be nicely preserved, right? Because the maps, the group homomorphisms are composed as maps. And since the maps stay the same, the composition will be preserved. And moreover, the identity elements, the identity morphisms will also be preserved, right? So if I take the identity morphism, which is given by the identity map, and I view this a pair group, I view it as a triple group. Of course, here it's the same, so I shouldn't write primes anymore. So this is an identity morphism in this category, and it will map to exactly identity morphism in that category, in the other one. So in other words, what we have is in each direction, we have the thing called a functor. A functor is a mapping of objects and morphisms that preserves domains and codomains of morphisms, which means that if a morphism goes from here to there, then it will map to a morphism going from whatever the first object maps to wherever the second object maps to. And also it preserves a composition, and it preserves identity morphisms. And when I have two functors going back and forth, so that the composites are identity, and this is not difficult to see that they are in this case. So here we have that, and here we have this. Right? If I take my because I had a bijection, right? So if I take this, I produce that, and I go back, it will bring me back to this. And so that's the same as not changing this. In other words, applying the identity functor to it. So we get an isomorphism of categories. We don't have an equality of categories, but we have an isomorphism of categories. And it happens very often in mathematics that we can specify mathematical structures in all sorts of different ways. There are many ways of formalizing the definition of a group. Here we have two different ways, but there are many other ways, right? Why should I write it as a triple this way? I could also write it as a triple this way, right? This will be another way of defining a group. I will not get a category that's identical to this one, but it will be isomorphic. So the notion of isomorphism of categories is definitely useful because I need to have a way of not seeing the difference between different ways of formalizing things. But there is a third, a weaker notion of sameness of categories that is very, very much needed and in some sense is more useful because, well, so it turns out that isomorphism of categories will preserve all the properties across from one category to the other. And that's for similar reasons why bijection, which is homomorphism in both directions, preserves all the properties of mathematical structures. But it turns out that you need less than isomorphism to ensure that all reasonable properties of the category are preserved, and that is the equivalence. And let's motivate that with an example, just as we did here. But before I move on to that, I hope this was, I think this was maybe a bit too basic, but is anything unclear here?
No, it's fine.
Yeah, everything's fine.
Fantastic. So now let's consider the category of vector spaces, let's say over reals. And these are finite dimensional vector spaces. So I'm going to put FD there. We consider the category of finite dimensional vector spaces. And let's consider the category of matrices over reals. I think we briefly touched on this category in one of the first lectures. So what is this category? Objects are natural numbers. 0, 1, 2, and so on. And a morphism from n to m is an m by n matrix. Composition of morphisms is defined as matrix multiplication. So if I have another number here, two matrices A and B, they're composite. B composed with A is defined as B times A. The usual way we multiply matrices. We get a category like this. Okay, what is this category? Well, objects are finite dimensional vector spaces. Have you already done a course on vector spaces, Alexander?
Yeah, of course. Actually, several times.
Yeah, sure. And you've certainly also learned about linear maps between them?
Yeah, of course.
Mm-hmm. So we get a category. Linear maps compose. Composite of linear maps is a linear map. We get a category. And I'm sure you also learned how you can represent a linear map as a matrix.
Yeah,
right?
of course.
Yeah.
Yeah.
But to do that, we first have to pick a basis in the vector space, right?
Yeah, so this isomorphism is not canonical, so to say, or natural, I think. I'm not sure.
That's right. So well, it will be natural, but it will not be an isomorphism of categories. It will be an equivalence of categories, in fact. So we have a functor going this way. The dimension functor. I take a vector space. I randomly choose a basis in it. So it requires making choice for every vector space. I choose a random basis in it. And then, well, before I choose the basis, I just look at the dimension of the vector space. That is invariant of the basis, of course. And that's the number I assign to my vector space. So vector space V gets mapped to n, which is the dimension of V. But now to to map the morphisms, I need to choose bases. So if I have a linear map, let's say L, once I choose the basis in V and in W, then we can represent the effect of what L does. We can represent it through a matrix. And this is something that you also remember, right, Kwatisa?
Yeah, it's what is it? Yeah, I remember some of it, but yes.
I think in one of the courses in Stellenbosch that I taught many years ago, we denoted it like this. How would you denote it in your course, if you remember, Alexander?
Well, our professor has, how to say, sorry, what was the definition about?
Yeah, so if you take a linear map, and
Yeah.
once you've chosen your basis in V and W, how do
Yeah.
you write down the corresponding matrix?
So the letter C, the base is down there as sub-indexes, and the map in the brackets. That's how Jan Schroer does it, for example.
Uh-huh. So we have, let me call this thing V prime. So we've got B and B prime here, and then you would put, is
Just
it like
a
this?
regular brackets, actually, but yeah.
Okay, regular brackets. Okay. So this is how they do it in Bonn.
Yeah.
Okay, fantastic. I think
So the notation you're using is it the one from linear algebra done right? Sheldon Exler, I think. The Kelly.
you even know the name of a book where they use the same notation, Alquatisa.
Yeah, well, it was I used to reference it frequently.
Uh-huh. Okay.
Okay.
Wonderful. And now that I remember better, I think the notation we used in that course at Stellenbosch University was this, and the square brackets were supposed to represent the brackets of the matrix, but doesn't matter. So the notation here is not important. Anyway, so we've got this process, and then one of the very important facts, of course, is that if I have two linear maps, L and M, and I compose them, and then produce the corresponding matrix, is the same as first producing the matrices and then multiplying these matrices. So we have a functor. Yeah, I hope the order of bases is correct here. I mean, based on the notation used. Okay, there we go. And so I can compose these linear maps, and they should map to the product of these matrices. So if this is my matrix A, and this is my matrix B, then it should map to B times A. But this is not the only fact we know about the story. The story goes further from, I mean, the story of linear algebra, the way you learned it. I'm sure you also had the following second ingredient of the picture. And I'm going to show you now that second ingredient is actually describing equivalence of categories. Let me just make this screen the right size here. So we now described a functor from back to the category of matrices, but there is also a functor going backwards. So this is this functor. Let's call it a dimension functor. There is also something going backwards. If I take a number n, I can map it to the vector space R to the power n. And if I have m here, I can map it to R to the power m. And then L can be mapped to R to the power L. What about the matrices? Well, I can pick the standard basis here, the one that has vectors where coordinates are all zeros except one where the coordinate is 1. And so I take that basis and I find a linear map for that basis that that would have given rise to the matrix A. So this is the linear map corresponding to A, and this is the linear map corresponding to B. And again, we have a functor here. But in fact, as I said before, we have something more. Namely, if I begin with my n, m, and l dimensional vector spaces, I could consider this r to the power the dimension of v, r to the power the dimension of v prime, and r to the power the dimension of v double prime. So what is happening here? I had this dimension functor, and then I had this exponentiation functor that I put, well, sorry, it should be this, r to the power whatever. And now I'm composing those two functors, right? I first apply the dimension functor, and then I apply the other one. And that's how I get this thing out of V, yeah? And as we know, we're not going to have equality here. So if these two functors were giving me an isomorphism of categories, when I go that way and I come back here, I would get the same vector space. In fact, that's what happens if I do it this way, right? If I begin with n, I take r to the power n, and then I consider this dimension, it will be exactly n. So on this side, I will have equality. So this composite here of the two functors, which then is the dimension functor composed with this r functor, this would be, in fact, equal to the identity of matrices. So we have some kind of partial isomorphism. We're on one side, we do have equality, but on the other side, we don't have equality. If I go there and I come back, so that's having a vector space, I take r to the dimension of the vector space. It's not going to be equal to v, but there will be an isomorphism between them. So these two objects are not the same object as they would have been if I had isomorphism of categories, but they're isomorphic objects, right? So these isomorphisms take place at each level. But moreover, these isomorphisms are nicely compatible with how the linear maps are mapped to matrices. So what does that mean? If I take a linear map here, then I could consider the linear map here that corresponds to the matrix C, B, B prime of L. So create the matrix first, then create the linear map between these standard vector spaces. And now I want to ask you whether or not your course included, and it most likely did, whether or not your course included this diagram saying that it's commutative. So that this composite will equal to that.
Yeah,
and maybe just it did. Okay, fantastic.
Well, actually, what I find really strange at on, even though it's first semester, there are a lot of commutative diagrams here.
That's wonderful.
Yeah, I would say.
No, I think you've got a really very high quality, high level education system there in Bonn.
Well, it is a case, but it's kind of hard to get used to doing so many commutative diagrams in linear algebra course. I mean,
I see. Yeah, I remember in my first year in Georgia many years ago, we also had very advanced courses. In fact, we had a lecturer in analysis who was Georgian, but he was raised in France. And he started off with the first lecture with the axiomatic definition of the real numbers. And I had seen some set theory before, and I've seen some axiomatic mathematics before, but most of my classmates had not. They just went out from school in Georgia, right? So everybody was quite shocked with that.
Sorry, do you mean Khvedri Nasaridze or?
No. There was somebody called, he's not alive anymore, unfortunately. He died of heart attack quite early. Somebody whose surname was Trebuchava. Was a very nice man. He was very distant from everybody. He would not be very social, but he was a very nice lecturer. Well, I liked him at least. And he was also a nice person. Anyway, there's something more to say about this commutative diagram, right? First of all, this isomorphism is not just a random one. It actually picks out the standard, it picks out the basis in here. So it's the one that maps the standard basis to the chosen basis B in V. And since we are now choosing basis, maybe I should add a subscript as an indicator which basis I've chosen, even though it's not part of the structures, right? So here we just have vector space without chosen basis, but we choose the basis to choose the isomorphism here. So if I were to write down the matrix for this isomorphism with the basis being B here and the basis here being the standard basis, what would the matrix for this isomorphism be?
Sorry, what was the question again?
So this isomorphism picks out the basis B here. So in other words, a basis vector of the form, let's say 1, 0, 0, 0, 0, will get mapped to exactly B1, the first element of this sequence B, the first term of B. So if I have an ith term, so I don't know if you remember this or not, but this is how this isomorphism works, that it does that. So if I have 1 at the ith position, it will pick out, so by this isomorphism, this will be mapped exactly to Bi. So if this is the ith position. And my question was, what would then be the matrix for this linear map? So how do we find the matrix? We take the basis vectors, right, of my domain. Okay, so I've now drawn it the opposite way, but it doesn't matter because it's an isomorphism. I have it both ways, right? So let's draw it opposite way now, just because I've done it there. So the question is, what is the basis representation of this linear map? The one that does this. What is the matrix representation of that? So how do I find a matrix representation of a linear map? The columns of the matrix will be where the basis vectors from the domain are mapped to, expressed in terms of the basis chosen in the codomain, right?
So will it just be an identity matrix here?
Yeah, exactly. It will be an identity matrix because so the ith basis vector, which is this, gets mapped to exactly Bi. But what are the coordinates of Bi in terms of the basis B1 up to B, whatever, Bn? Of course, the coordinates are 0, 0, 0, 0, 1, and then 0, 0, 0, 0, right? Does that make sense to you as well, Okotisa?
So it's a Bi by Bi matrix. Is that what you wanted?
No. Bi is not the dimension. Bi is the actual ith vector in the basis. So B, a basis, is a sequence of vectors, right? Let's say dimension is n. And Bi is the ith term of this sequence.
Okay, so notationally should be capital N subscript, your capital I subscript N.
Capital
That's
I.
the matrix. Yeah, for identity
Oh yeah,
matrix.
yeah. You're right. Yeah. So this will be represented by in that notation. It will be that matrix. Yeah. So this will be the matrix representation of this linear map. And so let me just quickly re-explain why. So how do we get a matrix representation of a linear map? Every column are the coordinates of where the basis vector maps to, right? And so the ith basis vector maps to bi. But what are coordinates of bi in this basis? Of course, it's exactly this. Zeros, one at the ith position, and then zeros again. And it's just a side remark that this matrix will have identity matrix as this linear map will have identity matrix as a matrix representation. So anyway, so these squares commute. The same happens here, of course. So if I have another one here, L, well, I called it M before. This will be commuting with this. And of course, that will also make the bigger thing commute, but that's not so relevant anymore. It's a consequence of the big one will also commute, right? Because the smaller ones commute. So what happens here is that on this side, if I compose these two functors on the other side, I don't get identity functor. Instead, what I get is something whose values are isomorphic to the values of the identity functor. So there are these isomorphisms. But these isomorphisms make such squares commute. They're not just arbitrary. This is called natural isomorphism when such squares commute. So this now leads us to the notion of natural transformation and natural isomorphism, and let me define what that is. And that's a very general concept that doesn't have to do with necessarily with endofunctors. So if I have two functors, I've got two categories, C and D, and I've got two functors, F and G, then I could define a notion of a transformation of one functor into another. Let's call this alpha. And it is defined as a family. So alpha is a family of morphisms, one for each object C of C. So alpha C, each alpha C runs from F of C to G of C. Where C ranges over the objects of the category C. So the family we have here is this. So this would have been alpha V, and here we would have had alpha V prime, and here we would have had alpha V double prime, where the two functors are the identity functor, so V equals to the identity functor of VEC applied to V, and this one is the composite of these two functors applied to V. So this dim composed with R functor applied to V. And now I'm considering a more general situation where I have two functors, their values on the same object C, and for each C, I'm choosing a certain morphism, and it doesn't have to be isomorphism. In this case, the alphas are isomorphisms. So the condition on this is that the following square must always commute. If I have FC and I have GC and I've got alpha C, I want this to be compatible with some other alpha C prime by moving between C and C prime via some morphism. So if I have morphism, let's say L from C to C prime, maybe I shouldn't call it, I want to call it L because I want to notationally link it with what we have here. So if I have a morphism L from C to C prime, I have f of L, and here I will have g of L. And what I want is see here, our L was this L, and so that's the same as identity functor of VEC applied to L, and this one is the same as this composite functor applied to L. So this must commute for every morphism L from C to C prime. Okay, so this leads us to this concept. A natural, yes?
What I always found strange here is that even so, as index, we have objects of category C. At the end, we have morphism between objects of D. So how should one see this?
Can you please repeat that?
It feels a bit weird for me that here, where we define alpha, we have alpha C. So C stands here for objects of category C.
Yes.
But morphisms are between objects of category D.
Yes.
So that's what's a bit weird for me.
You mean that each alpha C is a morphism inside D?
Yeah.
Well, this is how you can think of it. If I remove this arrow here, right? This will become equality symbol. Yeah?
Yeah.
So the ideal case is when I have two equal functors. If I have two equal functors and GC, you agree? So the values of the functor f and the functor g will be the same for every c. Yeah? So think of it this expression. Yeah? When you have an expression like this, an expression of equality of functions, you have the situation that for every variable c, you're saying that two values are equal, yes? Now, with a natural transformation, we have something more subtle than being equal. So the equality turns into a morphism. Now for HC, FC is no longer equal to GC, but there is a way to move from one to the other. Does this answer your concern?
Yeah, now it makes much more sense. Thanks.
Okay. A natural transformation. Yes, Okotisa?
So if a functor preserves domain codomain composition and then two functors are equal, so could you go deeper in terms of that definition of a functor? Like equality is saying what about the domain codomain composition, and what is the difference when you move to a natural transformation in terms of decomposing it?
So yeah, let me do that. Thanks. So if f and g were equal functors, then I would have equality here, and I would also have equality here. Now I can think of equality as a morphism, namely the identity morphism, right? Let's think of equality as the identity morphism, which is of course the same as g of c. What does commutativity of this diagram mean then? If I have identity morphism running here and there, then of course commutativity of this diagram would also force FL to equal to GL. Do you agree with that, Okotisa?
Yeah.
So I can express the idea that not only the values of the functor on objects, but also the values on morphisms are equal. I can express that idea by saying that I have these commutative diagrams with these being the identity morphisms. But with a natural transformation, they're not identity morphisms anymore. They're just random morphisms. We still keep the commutativity of the square.
Okay, yeah, I think that picture is much, yeah, it allows me to see it better.
Yeah, thank you very much. The very, very good questions. So a natural transformation from F to G is a family of morphisms, one for each object of the domain category. Is a family of morphisms in D such that let's call this star, such that star commutes for every morphism L from C to C prime. And this happens for every morphism in C, of course. Okay. Now that we have defined a natural transformation, so what does that mean? So the picture we get is that if I now consider two categories, C and D, and I consider functors between them, which are arrows between these things, right? Now I seem to get arrows between arrows, which are the natural transformations. And really, the intuition we expanded on before is quite nice here. So I can think of these natural transformations as a way of measuring the difference of outcomes between the two functors. But if I have two of them that are lined up like this, I can compose them, it turns out. How would I compose them? Well, let's draw. By the way, this square is called the naturality square. And we see that in the first year in Bonn, they don't teach the terminology and the category theory behind it, but they do teach these naturality squares for vector spaces. So do they in the second year at Stellenbosch University in the linear algebra course. So let's draw this naturality square for alpha. FC GC and we have alpha. I think I would need more space in the other dimension, so let me draw it down here. FC prime GC prime. So we've got this alpha C, we've got alpha C prime, and here we have some f of some L, and this is G of L, right? This is the naturality square for alpha. Now let's draw for beta. In fact, the one for beta can be drawn right next to it. This is BC, that will now move from GC to H of C. And this will be H of L. And so this is our two stars, right? So this commutes. we know, and also we know that this commutes. Now, what about a possibility of composing alphas and betas? You see, alpha C, each alpha C is a morphism from FC to GC, right? And each beta C is a morphism from GC to HC. So they can be composed, right? So we could try to draw a third diagram where now I move directly from F of C to H of C by the composite of these two. So beta C composed with alpha C. And here I have F of C prime, H of C prime, where again I do beta C prime composed with alpha C prime. And here I have F of L, and here we have H of L. The question, would this diagram commute? Well, the new diagram we drew is actually the outer rectangle in the previous one, right? So this is going all the way across here and going all the way across here. So now we want to know whether going this way and there is the same as going this way and there. But we know that each of these commute. So of course, going all this way is the same as going this way because of commutativity here. And then that's the same as going this way because of commutativity here. So do you agree with, do you see this, that this also commutes?
Yep. Isn't it like a
Yes.
general case if you have two squares and
Yeah,
what's
that's right. In fact, if you patch commutative diagrams with each other, everything will commute. The outer diagrams you form will commute. It's a very general phenomenon. Ekotisa?
Yeah, sort of diagram chasing, I think, right?
Yeah, that's often called it that way, yes.
Okay.
Diagram chasing means something a bit more than just commutativity, but yeah, we can also call it like that. Okay, so we get a composite natural transformation, beta composed with alpha. And then I guess you see where I'm going to, right? So the previous case we discussed where I said that these things are identities will give me identity natural transformations. And here is when the where the fun comes. The category of functors, we get a category of functors from C to D. So this thing is a category, it turns out. So functors from one category to another category themselves form a category where the functors are the objects and the morphisms are natural transformations. This shouldn't be too surprising. We've seen this before in mathematics. If I take two vector spaces, right? Linear maps between them form a vector space, don't they? Yeah, you can multiply linear maps by scalars by scaling every value. And you can also add linear maps by adding them value by value, right? So it happens sometimes in mathematics that you take all morphisms between two structures, and that itself has a similar structure. The structure is inherited from the codomain. By the way, this links very much with what we discussed in the previous lecture, this idea of exponentiation. Usually, when this is the case, it means that you're able to exponentiate your objects inside your category. But we're not going to go into that now. So functors from a category, and just like in any category, I can consider the notion of an isomorphism, right? So what would be an isomorphism between two functors? Well, an isomorphism will be a natural transformation, alpha. So this will be called the natural isomorphism. A natural isomorphism of functors is an isomorphism in a functor category. So in a category like this, so this is called a functor category. And now we can go back to vector spaces and examine what happens there. So, sorry, I was explaining what it is, right? So if I've got two functors, f and g, a natural isomorphism will be a natural transformation alpha, such that there is a natural transformation going backwards, such that each composite is identity natural transformation. So value-wise, this means that it basically, value-wise, it turns out that it just means that each alpha C is an isomorphism. You can prove that if each alpha C is an isomorphism, it will be a natural transformation. The inverse will also be natural, it turns out. And kind of a ghost of this fact would have been also proved in the linear algebra course for that specific diagram. So I've got this alpha C here. I've got the beta C going backwards. And what we're saying here is that each of these composites are identities. So let me add this remark. This is equivalent to requiring that each alpha C is an isomorphism, which is exactly what happens in the vector space case. So not only I have these commutative squares, but each of these are isomorphisms. And then, of course, because the square commutes leftwise, then if I draw these inverses, then it will also commute the rightwise. It's just a simple discussion about commutativity and isomorphisms. So you get that the inverses also form a natural transformation, and that's how one proves the yellow remark I made earlier. So what it means here on this side is that although on this side, when we compose these two functors, we do get the identity functor on the category of matrices, on the other side, when we compose these two functors, we don't get an identity functor, but we get something that is naturally isomorphic to the identity functor. And that is what is equivalence of categories. So the general definition is the following. I think I need a bit more space here. Two categories, well, an equivalence between categories C and D is a system F consisting of F, G, eta, and epsilon, where F is a functor from C to D, G is a functor from D to C, eta is a natural isomorphism from identity functor of C to the composite GF. So this is a functor, and this is a natural isomorphism. and the epsilon one is the one from the other way around. So FG to identity of D. So this is the natural isomorphism. So if I put all of them on the same diagram, the picture would be like this. I've got C, I've got D, I've got the two functors, F and G. I've got their composites. So here I have the composite GF. Here I have the composite FG. And then I can also draw the identity morphisms functors here. Okay, I think I need a big separate picture for that. Sorry, let me make a separate picture for this. Big one. We've got these two functors. Then I've got the identity functor here, 1C. I've got the identity functor of 1D, but I also have the composites of these two functors. So this is F and G. So this is FG, and this is GF. And what I'm saying here is that in this direction, I have this eta. In this direction, I have the epsilon. Of course, the directions of eta and epsilon are less relevant, maybe, because they end up being isomorphisms, so I will also have their inverses going the other direction. But there is a notion of an adjunction, which is a bit more general than an equivalence, where the directions start to matter. So that's why I'm putting it this way. And what we saw in the case of vector spaces and matrices was that on this side, so we had matrices on this side and vector spaces on this side. And on this side, we actually had this being identity. Actually, the way we ended up drawing the thing was flipped around. So we had an isomorphism here, which was not identity, but on this side, we had an identity on the side of matrices. So it was kind of degenerate equivalence, where on one side it's like an isomorphism, but on the other side, it's not. Of course, if I force both of these to be equalities, then I get isomorphism. And that's the whole idea, right? So when we now compare categories, because we have these additional arrows between arrows, we can do some more subtle things than just requiring that this composite must be identity and the other composite must be identity on the other side. And this notion, to those of you familiar with homotopy theory, right? This notion should look very similar to the idea of two spaces being homotopic to each other, where you can have continuous maps going back and forth, and then you go forward and then backwards. That composite is not identity, but it's homotopic identity. Any questions on this concept of equivalence, as far as we discussed it thus far?
Yeah, maybe you will talk about it later, but still, are there any properties of objects that natural transformations respect, so to say?
You want properties of objects that natural transformations respect?
Yeah, one can say so.
I'm not sure one can say so, because remember, a natural transformation for each object picks out a morphism, right? We can talk about functors preserving properties of objects, because functors map objects to objects, right?
Yeah.
And then I can talk about how the natural transformation, maybe if let's say, if I go back to this picture.
Well, I mean, like, natural transformation is a kind of morphism between two functors, f and h. And
yes.
Let's say we pick some object in category C, let's say A. So A gets mapped to category D, namely, we will get the f of A and hash of A. So my question is, how are these two objects related? So how close they are to...
The answer is the natural transformation, right? So one way of relating them is to identify a natural transformation between the two functors. So the relationship between the two objects is given by the natural transformation. You can think of alpha as describing how FC and GC are related with each other. So we have two categories. We have an object C here. We map it by the functor F. We map it by the functor G. And now your question is, how are FC and GC related with each other? Well, that question is exactly what motivates the definition of a natural transformation. We want them to be related in some way. So there to be a morphism between them. Does that answer your question?
Could we use an example? I don't know. So if it may be a category of vector spaces and matrices. When we abstract to the level of natural transformation, using that example, what is happening? Or any other
Just
example.
one second. Yeah, sorry. Okay, so let me draw that picture, that example in a similar picture as this. So we have, let's say here, the category of vector spaces. And here, also the category of vector spaces. And if I have a vector space V, I can assign to it itself. Rather, let me do that on the bottom side. I can assign to it itself. So that's the identity functor. Or I can assign to it R to the power the dimension of V. Yeah?
Okay.
And then we spoke of this isomorphism that we have, which we now can call epsilon V, that maps a vector in here. So it will map a vector of the form x1 all the way up to, let's say, xn, to their linear combination in the basis of V that we've chosen. So it maps that to that. So when I choose my basis in V, I can represent every vector in V as a tuple of numbers, right? And these tuples of numbers themselves is a vector space, R to the power n. And those two vector spaces are in bijection with each other. Moreover, this bijection is an isomorphism. So that's my epsilon. Is that what you were after?
So the thing at the bottom, the sum at the bottom, is it still, what is the dimension of V as at the bottom there?
N. So n is the dimension of V.
So they have the same dimension, that's fine.
Yeah.
Okay, yeah. Maybe if you continue, I can start piecing it together better.
Mhm. But let me first go back to Alexander. So Alexander, did I answer your question? I think that maybe you wanted something else than what I said.
Yeah, kind of, but it's fine, I think. So, like, my question was like, if you have two functors, let's say two groups, and they're naturally isomorphic, what can we say about groups that we get from these functors? Like, how are they related to each other? Are they isomorphic or?
Your starting point was that we have two functors that are naturally isomorphic, right? And then you said, let's say two groups.
Sorry, no, let's say not naturally isomorphic, but let's say there is some natural transformation between, not necessarily isomorphism.
Right.
Yeah. So are there like any nice properties, let's say in concrete categories, in categories of algebras or something like this? So it's just to, I don't know, functors share?
Yeah, so so my answer to that is that whatever things they share, the purpose of natural transformation is to identify that. Like for example here, these two values of these two functors, they share something. In fact, they're isomorphic, these values always, and the natural transformation describes that, the thing that they share. But maybe it will be useful to give you an example of something, of a natural transformation that is not a natural isomorphism. And maybe that will make things a bit more clearer.
Yeah, that would be nice.
Mm-hmm. Okay, so let's look at, so we kind of define natural transformations in order to define a natural isomorphism, but now it's time to look at examples of natural transformations that are not natural isomorphisms. Okay, so one thing we can do is to consider, and the examples are many, of course. So but let's consider something basic. So let's take the category of sets on both sides, and let's take two functors. One is the power set functor, so it maps x to the power set of x, which is the set of all subsets of x. So it's all s's such that S is a subset of X. And the other functor is power set composed with itself, so double power set, p squared. So it maps X to double power set of X. Which will be now all subsets of the power set, right? So for example, if I take the empty set, let me make this a bit smaller. If I take the empty set by the power set functor, it will be mapped to the singleton set, right? By the double power set functor, it will be mapped to two-element set, consisting of the empty set and the singleton set, because these are the two subsets of this non-empty set. Okay, now we want to ask this question, the one that you're asking, Alexander. So what do p squared x, do p squared x and px have anything in common? Do they share anything?
Well, the elements. not really elements, but
not really elements, but
yeah.
something else, right? So
Yeah,
let's try to identify what that something else is.
Yeah, good remark. If you like flatten our set, if you remove all the brackets,
Fantastic, fantastic. So that flattening will be a natural transformation. And that's called union. U, UX. So what is flattening? So I have a, what is an element? Let me describe an element of double power set. An element of double power set has elements, right? What are elements of that? They are subsets of the single power set, right? So each of them are elements, are subsets of X, right? So maybe some of them overlap. So this is X. This is some element A of P squared X, and these are elements of Px. So by flattening, what you mean is we consider the union of these things. Isn't that what you mean?
yeah, exactly.
Mm-hmm. And then we get a single element of Px. Okay, so algebraically or symbolically, if I had something like the set of AB, so this is one subset of X, maybe this is another one, and maybe this is a third one. We want to create a single subset of X out of all this to flatten this thing. And the answer in this case will be A, B, C, and D. So the question of what do these things have in common, so to say, is answered by this idea of flattening, and now we will see that in fact this is a natural transformation. So that brings back to my answer to your question, which says that when you want to know what the values, what two values have in common when you have two functors, right? An answer to this question is something that's described by a natural. So whatever the commonality is, it will be described by a natural transformation. That's the philosophy. So basically, the purpose of natural transformation is to describe what the two functors have in common, or the values have in common. So we have to prove this commutative diagram, right? So if now I have a function from X to Y, let's call it f. I haven't described to you how we define these as functors, but let's do the obvious thing. We just take direct image under a function. So my two functors are p squared x and px, and I've got this ux here. Here I have p squared y and py, and I've got the uy. Here I have p squared f. What does it do? It applies f to every element of every element. So so an element of double power set of X is a structure of this form, right? And we will apply f to each single component here at the base level and map them wherever they map to, and then construct the corresponding structure on the other side. So that's what the p squared f does. And we've got something similar here, pf. Now let's check that this diagram is commutative. So I'm going to take an element in here. Let's call it R. So let's say R is an element of double power set. Then what will be, let's compute what is this composite. So what is going to be ux applied to R? We have to flatten this R, right? So it's the union of all elements of R, right? So these are the all elements of X's such that there exists an element, let's say Y of, no, not Y, sorry, an A of R with the property that X is element of A, or rather, that exists A such that X is element of A and A is element of R. Is that what I want to say? Yeah. No. Yeah. No, I think that's what I want to say. So going back to this picture, how do I describe this union? What are the X's in there? X's in there are things for which there exists an A that is an element of, okay, now I'm calling this thing R. So there exists an intermediate A, so that small x is an element of A, and A itself is an element of R. Okay, so this is union applied to R. Now, what about PF applied to it? So what is going to be PF applied to this? Now we need more space. Let me copy this entire thing to the side. So I need to take, so in general, maybe we should write down what is PF of some subset A of X. So let's say A is a subset of X, or in other words, an element of the power set of X. What is PF of A? It's the usual thing we write as F of A. So it's all the set of all F small a's where A is in A. So that's what we want to do here. We want to do the set of all F of X's such that X comes from here. So in other words, there exists A such that X is in A and that is in R. There we go. So we've computed what happens to, if I pick an R here, we've computed what happens to when I map it there. And then I further map it down here. This is what happens to it. Now, what about the other way around? So what if I map it first here and then I try to map it there? What will I get? So let's now compute p squared f of R. This will be just f of R. So I need to apply f to each element of R. So it will be the set of all f of a's, where a is an element of R. And that itself will be just inserting f inside A, so applying f to every element of A. So that will be the set of all sets of the form f of x, where x is in A, where A is an element of R. Yeah? So we're now here. That's where R is mapped to by p squared f. And now let's flatten afterwards. So now we have to apply u to that. So uy applied to p squared f of R. What is that going to be? So I need to flatten this, right? But don't you agree that just means removing these brackets, right? So I've got these sets, and I take their union. It's the union of this thing, which means union of the elements of that thing. And of course, it will be all these kinds of fx's. So it will be the set of all possible fx's such that I can find an A where x is in A and A is in R. So there exists an A such that x is in A and A is in R. So we see we get exactly the same thing as we got. So when we ask this question, what do the double power set and the single power set have in common? We observe that, okay, so we can do this flattening, and that kind of describes what they have in common. And now what we're saying is that this flattening process is compatible with the values of these functors at morphisms. So in other words, each of these squares are commutative. If your question now is, why is it useful to know that squares like this commute? Then the answer to that would be, well, I mean, the simplest possible answer would be, well, if and in those cases where these things are isomorphisms, so if you've got two functors that are naturally isomorphic to each other, knowing that they're naturally isomorphic to each other, you can transfer properties of one functor onto another. So if you know that one functor behaves well, whatever it means, it may maybe preserve some nice properties of the category. And if it's naturally isomorphic to another functor, then you will know that this other functor also behaves well. But if it's not an isomorphism, it's just a natural transformation, maybe some conclusions can still be drawn about the other functor, but of course, it will not be as powerful as if it was a natural isomorphism. Just like with morphisms between structures, right? If I've got a morphism between structures, some things are inherited by those morphisms, but not everything. Everything happens only when there's an isomorphism. Okwatisa, did you want to ask something?
Yeah, in the diagram you said p squared and then down is a p squared y. So is a y, and also you said f of a. So is y the range of f of
Not
a?
necessarily. Y doesn't have to be the range of f. So it could be larger than the range of f. So y could have elements that are not coming from x by f. F
But
doesn't
we
have to be a
define,
surjective function.
okay. But we defined what? We defined p of a as f of a.
Yeah.
Hmm.
So this will be a subset of p of y, right?
Yeah, yeah.
In other words, an element of p of y. And so pf will be a map from px to py, which maps a to f of a.
Okay, okay.
All right. Now, we've actually arrived to a concept, this concept of natural isomorphism, that was the starting point of category theory. And let me share a different screen to show you something here. It's still opening on my side. Can you see this?
Yeah.
Yes.
So what is this? In the title there, you see general theory of natural equivalences. What they mean by natural equivalence there is what nowadays we call natural isomorphism. So it's a paper about a general theory of natural isomorphisms. In fact, this is the first ever paper in category theory. This is the paper that introduces the concept of a category and a functor, and from which the subject grew out. So as you see, this idea of natural equivalence was, I mean, we arrived to this at the end of our lectures, but this was actually the starting point of category theory historically. You probably know already the history, right? Samuel Eilenberg was mainly a topologist, and Saunders MacLean was mainly an algebraist. And they collaborated to identify some common ideas emerging in algebraic topology. And they eventually came up with this idea of natural equivalence. And they wanted to describe it properly. And to describe it, they had to define functors, and they had to define categories. And then in the paper, so let's actually go through the contents of this paper and link it with the course. The first chapter of this paper, you see, the papers usually don't have table of contents, but because this is a longish paper, and because this was supposed to be some kind of foundation to these new ideas, it was useful that they presented the table of contents. The first chapter gives the definition of categories, examples, and functors, and then examples of functors, and then slicing of functors. This is something we haven't talked about. And then looks at the question of foundations, which is important because categories are larger objects, right? The collection of objects in a category do not always form a set. Like the collection of all sets, which is the objects in the category of sets, will not be a set. So I think that's these kind of foundational topics they discuss here. Then they introduce this idea of transformation of functors. So these are the natural transformations, and give some examples. Also, okay, categories of functors. This is something we did today. Composition of functors. They do composition of functors after the other one, because inside the category of functors, functors are objects, right? You don't necessarily compose them. You can compose transformations between them. And then this is interesting, construction of functors by transformations. Kind of these natural transformations are used as a tool for building functors from others, I guess. I wouldn't know what this is unless we look at it. I don't remember this one. Then there is this interesting kind of application. So they describe this idea of quotient functors and subfunctors, and link it with, and they have these isomorphous theorems between four categories. So isomorphous theorems are usually stated for algebraic structures, but you can also do for many other kinds of structures. And I guess they look at it for categories. So every functor will have kind of image, and just like the f of a we were discussing, you take a category that's a functor from one category to another. You can consider all the objects to which these objects of the first category map to, and then try to generate a category on the other side that would be the direct image of a functor, and then you can formulate isomorphous theorems as well. Anyway, then it goes on. Here we have projective limits. This is where these special kinds of limits called projective limits are defined. So this links with our notion of when we define limits and colimits in a category. The notion of product and sum isn't defined yet in this paper. That will be defined in the follow-up paper by MacLean in 47, and then more expanded in a 1950 paper. This is 1945 paper. It was presented to the society, I guess it's American Mathematical Society, 42, and then received for publication in 45. And then at the end, there is some applications to topology, and these would be, I guess, where they were the area by which they were motivated to introduce these concepts. And then the appendix is about representation of categories. It turns out you can embed every category into the category of large sets. Later on, a much more effective embedding was found. It's called Yoneda embedding. So people forgot about this specific embedding, but this is also a nice way of thinking of every category as living inside the category of sets. Anyhow, so you see that a lot of things in the course that we did in these 10 lectures can be found here. And so my suggestion would be, if you're interested, to look at this historical paper, that to do so, I hope that the background from this course would be useful for you to follow the paper. There is an interesting anecdote. One of his later papers, MacLean says that according to Samuel Eilenberg, this was meant to be the only paper in category theory. Well, the term category theory didn't exist then, but the only paper on categories. And then he says how wrong Sammy was. Sammy was a nickname of Samuel. How wrong he was, because indeed the topic flourished into not just something that was very applicable to other areas of mathematics, but also into an independent field. A large part of this flourishing happened through the students of Eilenberg, but also corresponding with MacLean. They developed a lot of the theory of categories. Okay, so let's go back to my board, so that if you have any final questions on what we discussed at the end. I do realize that the end was a bit maybe technical. I'm not sure to what extent this computation here was straightforward. Do you see my board again?
Yeah.
Okay.
So in terms of like research areas which are not like, because what is I'm looking at the paper you just showed us here, that you can study categories theory for its own sake, just to kind of get more theorems in an abstract way. But which areas have category theorists not really worked on? Like groups is the first one, I think, where we kind of saw applications and topology. But which other ones?
Well, are you asking which areas are those that still needs to be explored, or which areas have been explored?
Still need to be explored.
I think one of the fundamental goals of mathematics altogether is to apply this abstract understanding to be able to tackle concrete problems as well, right? A lot of mathematicians are motivated by this idea that, not all of them, some of them don't care about applications at all, but many mathematicians are motivated by the idea that eventually through mathematics we can understand the entire universe. And of course, there are many examples of that. I mean, modern physics, and not just modern, right? Physics always relied heavily on the mathematical language, and many mathematical ideas actually are motivated by physics as well. So when you do abstraction, you want to hope that you will be able to unravel concrete things in a simpler way, and in some cases maybe solve problems that haven't been solved before. There are a few topics in mathematics. So let's not talk about applications of category to real life. That there are people who also are passionate about that. Let's just talk about applications to mathematics. So there are a few topics in mathematics which are yet to be seen whether the abstract language of categories is powerful enough or not to, or rather how to. So the hope is that it is powerful enough, but the question is how to apply it, to unpack those things. In group theory, the very technical results of group theory, which begin with Silo theorems and eventually end with classifying finite simple groups. But of course, we don't know classification of all finite groups yet. So that classification of finite groups is very, very technical, right? It doesn't always use abstract methods. Already Silo theorems is something that is a bit of a mystery how to approach it using category theory. There doesn't seem to be a very elegant abstract approach to Silo theorems yet. So that would be one of the topics that one we want to look at. But then the idea would be, the goal would be eventually to be able to capture the essence of, let's say, the most technical results on which the classification of finite simple groups builds. Another field of mathematics where applications of category theory are useful and where more applications would be desired would be algebraic geometry. So algebraic geometry studies geometric objects that are given by systems of polynomial equations in the simplest case. This field is very highly developed field. It's actually also considered as one of the mainstream fields in modern mathematics. The modern algebraic geometry rests on the language that was developed, not just the language, but also the theoretical landscape, as they say it, by Alexander Grothendieck. And so what Grothendieck did was to apply category theory in unpacking the most central and the most fundamental concepts of algebraic geometry. And that later led to a number of big achievements in the field that was also celebrated by awards of various Fields medals, including Grothendieck himself. But Grothendieck's original dream wasn't fully realized. He had this dream of abstract algebraic geometry. And there's something called Veil conjectures that was a very hot topic in the second half of 20th century. It goes back to previous fundamental questions. And a student of Grothendieck eventually managed to solve those conjectures, partially based on Grothendieck's ideas, but not fully. And Grothendieck wasn't happy with those solutions. He said that there should be more abstract methods developed rather than finding some tricks to eventually solve the problem. So fully realizing Grothendieck's original dream to make algebraic geometry even more abstract in the sense of having those complicated problems, solutions of those complicated problems coming up completely out of general understanding of the landscape, is another area which is open for exploration and hasn't been completed that yet. In fact, there is some kind of pause on that. People have almost forgotten about Grothendieck's original dream. They often talk about this when they talk about Alexander Grothendieck, that he had this idea, but then eventually the problems were solved using more concrete techniques, and so it's not clear whether Grothendieck's original ideas work or not. But of course, it's a task of category theory to clarify that. So that would be another direction. And there are more connection between.
So differential geometry.
Yeah, the differential geometry is another area which makes heavy use of category theory. Well, some part of it, not all of it. Algebraic topology makes use of category. Modern algebra. I've got a friend, actually, Alexander might know him. Irakli Pachkoria. Do you know Irakli, Alexander?
Yeah, of course.
Yeah. So our fathers are close friends, and also his father is also a mathematician. Anyway, so he tells me that modern algebraic topology fully rests on the language of category theory, and there are many problems to solve there, but they don't necessarily solve it using abstract techniques, but they use the abstract language to think about these problems and formulate them and so on.
Okay, no,
The differential geometry
Yeah.
is one, algebraic topology is another one. But in the end, it's the fundamental question in the end is, to what extent can an abstract approach to something, where abstract approach means that you see the bigger picture, to what extent can that cover or subsume the concrete specifics of various concrete things? And
Yes.
my answer to that kind of, it's not an answer, but rather a hypothesis, I suppose. But my impression is that, like in everything in life, there is a balance. I think that there are certain things that you can understand using, you can fit into a bigger picture, but there are certain things that are really specific to the concrete situations. And for me, as a category theorist, the goal is to distinguish. So what is fundamental in a given mathematical topic? What can be viewed through the lenses of bigger picture, and what is specific to the given phenomenon? So distinguishing these two things.
Okay, yeah.
And the idea is that when you unpack, when you extract the bigger picture part of things, then you kind of enrich your tools further to allow you to understand other topics as well. So that's the benefit of abstraction, that you develop tools that are applicable also in other areas. By focusing on one problem, you develop general tools that can be also useful in another problem. And modern mathematics is a good example of this, where the fields we mentioned before, algebraic geometry, algebraic topology, differential geometry, and so on, they have some things that, some knowledge that gets used in another area to solve problems there. But Fermat's solution of Fermat's law theorem is a good example, where a lot of algebraic geometry and also some category theory as a consequence has been applied to eventually solve this long-standing problem. Not that solving problems, I don't see that as the main goal of mathematics. Personally, I don't see that. But of course, when that happens, it is kind of a witness to the fact that the theory has become mature and fruitful.
So I think like one of the funniest examples I think we have considered in the last category theory course last year, I'm not sure, was that abstract nonsense proves that topological groups have a billion homotopic groups. So what we do there is that we show that group objects in category of groups are a billion objects, and group objects from topology space, so topological groups simply said, have to be mapped to group objects again. And kind of with this abstract nonsense, we prove this sentence that topological groups have a billion homotopic groups. So we don't really do much but use this abstract nonsense kind of.
Yeah, it's a bit like technology, right? So before planes were invented, to go from one continent to another, it was an effort. It still is an effort for the plane, but you don't feel it because you're just a passenger, and you just go onto the plane and then depart the plane at the end, unless there is turbulence or the plane crashes or something like that. Then you feel that actually there was something complicated going on there. So when your abstract tools do not apply, sometimes your abstract tools are inadequate because they haven't been fully developed. Then you realize how complicated things could have been if we didn't have these abstract techniques.
Yeah, when Alexander was talking about a billion, it reminded me of when I don't know the specific example, but we were trying to construct a tensor, and then But the structure which we were talking about was not abelian, and you what is something which I found very interesting. You can abelianize a group which is not abelian already, and then somehow through what is it, rigorous mathematics, make an abelian group from that, and then get your tensor product in that way. So that's that was a very fascinating way of doing something.
Yeah, there are many constructions like the abelianization and many others that are nicely captured by these universal properties, which allow you to avoid the technicalities of the constructions. But anyhow, I think this is the end of our lecture. Any last questions before we say goodbye?
And not really.
Yeah, I don't have any at the moment.
Okay, fantastic. So thank you very much for your dedication, for always being here. It was without you, the lectures wouldn't have taken place, of course. Thanks for that.
Thanks you to Zurab as well, because every year this category theory course is something different this time as well. So I think it was less technical than last time, but it was more philosophical on the other side. So I still had fun.
Yes, and of course, you are the one who like makes it all happen. I'm sure if it was just the two of us, I don't think you are the glue who holds it together. Yeah, so yeah, as much as you would like to thank us, I think we're grateful to you.
Yeah, and we should also thank, well, thank you for that, and we should also thank NITheCS, the National Institute of Theoretical Computational Sciences, whose idea is to run courses like this. And so without them, probably this wouldn't happen either. Fantastic.
Yes.
I'm going to stop the recording here.